Very useful. You could taper a fiber in this way. You have your fiber, you attach it to two moving stages, and have a flame that moves to and fro in the middle. All of this under computer control. And with this type of tapering equipment, you can work with centimeter lengths, maybe 10, 20 centimeter lengths of fiber. You can do all sorts of different scales of lengths. You can make axial structures. You can make the structure of the fiber change with position. So you can make transitions. It's fairly quick, and you don't have to use a huge amount of fiber. And to some degree, it preserves the nanostructure as well. You can actually preserve the structure of the fiber. You can do other neat things with heating the fiber up to the softening point of the glass. You can kind of anneal it, and this makes the holes collapse at a very controllable rate, so you can change the geometry of the structure locally. You can also twist the fiber while you're pulling it to make twists in the fiber structure. You can also apply pressure to the holes and make the holes grow up in size. So there are lots and lots of things you can do with this type of technique. One of the things that Tim Burke's demonstrated now quite some time ago is shifting the band gap of guidance. So he started with a hollow core fiber that had a pass band in the infrared, and this was an optical picture of the transmission of light through the fiber in the infrared. Of course, you don't see very much because it's a wavelength the camera can't see too well, but that's what it looked like, with white light coupled in at the bottom. There's something in the core there. It's guiding at about 1500 nanometers. And then he tapered it, and he tapered it at fairly low temperature and very fast, so cold and fast. And this preserves the structure pretty well. So first of all, he tapered it down to guide 760 nanometers light, by a factor of 2 roughly. And now you're getting 760 nanometer light guided in the core. Of course, you can hardly see it again because the camera doesn't actually see it, but it is transmitting that wavelength. And then you tapered it some more down into the red, and now you can see the color in the core. The band gap is shifted to the red. Tapered it down to 620. Now it's starting to look sort of orangey yellow, characteristic of that wavelength. Now it's starting to look kind of yellowy green, 585 nanometers. Tapered it down further into the green, 555. Down to 505 is looking nice and beginning to look nice and blue. 440 is looking intense blue, deep blue, is characteristic of that wavelength. 400. The camera can't see it anymore, but there is light in the core. You're also seeing an interesting surface state forming at this wavelength. But I think it's quite remarkable that the tapering, given the complexity of the structure, that you can reduce it in size and still get some guidance. So that's something you can do with the band gap. You can also play around with the core size. So one question that one might want to ask is, how could you achieve zero dispersion wavelength at 532 nanometers? And this requires, if we look at the calculation, if we want to have a zero dispersion wavelength down at this short wavelength, you need to be able to make very narrow cores, 500 nanometer diameter, which is difficult to do using the fiber drawing process, and also very difficult to launch light into. If you want to launch light into such a small core, it's very difficult with lenses because it's so small. So one way to do this is to taper the fiber. So you start with a structure which has a reasonably large core, and you taper it down to 700 nanometers and 500 nanometer core size, and you preserve the structure quite well. And the nice thing about this is that the input coupling is 3 microns in size, and you taper down to the very narrow core with very good efficiency. The light goes into the narrow core and then comes out of the large core afterwards. So it actually works very well. You can generate a supercontinuum with this, and this is the pump light in the green at 532. That's a double microchip laser, frequency double microchip laser. That's the white light coming out, and these are just the different colors with filters, just to show that this works quite well. It's also dramatic, I think, to see the scale. This is what we started with, and this is the smallest fiber that we used. It's really quite a dramatic shrinkage in the scale. Just finally, one little thing you can do is make a rocking filter. We put a motor on the end here, and we rock the fiber to and fro. And while we're rocking the fiber to and fro like this, we scan a CO2 laser along the fiber. And this has the effect of inducing a rocking filter or a salt filter, which can be used for a polarization coupling from one polarization axis to the other of a fiber fringing fiber, a polarization maintaining fiber. this turns out to work very nicely. Here are some results for the conversion efficiency versus wavelength for one of these rocking filters. You get a sharp band of coupling. So the polarization state is coupled to is the opposite from the polarization state that goes in. And in this particular case, the device worked quite nicely. So this is just a couple of examples of the things you can do with the fiber after you've actually made them. Okay, that brings me now to just to try and summarize everything, or say some general things. It would be interesting to be able to look into the future, because I think there's a possibility that hollow core PCF might end up being used in telecoms. Maybe with a new transmission window, that's to say, operating at a slightly longer wavelength than the wavelength of existing telecom systems. I also think it's possible with this supercontinuum and nonlinear wavelength conversion that we can design fiber devices that will convert the wavelength of light from a laser source to almost any other desired spectral region. So for example, if you wanted to work with in a microscope and you wanted bright light in the blue, it may be possible to get efficient conversion to the blue using a very special design of fiber. It's also very exciting and interesting to think about making these fibers for the ultraviolet and the infrared wavelength ranges, but they don't exist there. The ultraviolet, let's say below 300 nanometers wavelength, infrared being beyond 2 micron wavelength, because there are many, many applications in those spectral regions where fibers would be very useful. And there's lots of work on high power lasers and amplifiers using some of these microstructuring ideas. I've mentioned gas laser devices. To me, this is both scientifically fascinating, some fundamental new experiments you can do. I didn't mention high harmonic generation, X-ray generation from laser light. There's a lot of fundamental physics, but also some very important technological applications. For example, sensing, environmental sensing for nasty gases in the atmosphere. You can use these long hollow core fibers for that. And you can make different kinds of mode converters. I mentioned that in the last part of the talk. You can make hybrid structures containing metals or semiconductors or liquids or other materials, maybe liquid crystals, of course. There are possibilities for new kinds of optical sensors, and also I didn't mention chemistry very much, but you can do chemistry on a very small scale with tiny volumes of liquids in a very well-controlled way. And we're doing some experiments here with chemists in this area, measuring things that they weren't able to measure before. And I mentioned long-distance particle transport, and of course there are probably lots of other applications. And it's up to people like you to dream up some of the new applications as to what's behind those question marks. And maybe in the future we'll see some even more exciting things come out of this work. So thank you for listening to me for so long.
Questions? Yes?
What's the material of the guided particle in the what's the material of the guided particle?
So the material of the
particle guided in the
of the particle, yeah. That was a silica sphere.
Is it possible to let the particle be made of metal?
Yeah, you could make. Well, yeah, that's an interesting question. Let me go back to the picture. Let's get that picture. Yeah, shut up. Okay. It's just I want to get the picture of the launch. This one. Yeah. These computers are too intelligent. Or too impatient. Yeah. This was a silica sphere. So this particular experiment will work for dielectric materials, because a dielectric material feels a trapping force that pushes the dielectric towards the high intensity region of the mode. So it gets pushed towards the center of the waveguide. If you put a metallic particle in, then it's more than likely that the metallic particle gets pushed away from the high intensity region. The reason is that the metallic particle doesn't have any resonances, except of course where there's a plasmon resonance. And if you're sitting at a plasmon resonance of a metallic particle, it would get pushed. It might get pushed towards the center. Depends a little bit on the forces and so on. But the sign of the trapping force depends on the material as to whether it's a metal or a dielectric. So in fact, you can do an experiment where instead of exciting this mode, you actually excite a donut mode, a mode that looks like a ring of high intensity, which has a dark region in the middle. And if you launch a metallic particle into that, the metallic particle will be trapped in the middle in the dark region and get pushed away from the bright regions. But it can't be pushed along because there's no radiation pressure, so it will just sort of sit there. If you want to push it along, you have to come in with another wavelength of laser light to push it along inside this kind of ring of light. So you could have two independent wavelengths to control it.
What powers have been used for this particle guidance? What laser powers?
What laser powers? Yeah, I've got the laser powers on this particular case. The powers are from tens of milliwatts up to, the highest here, a couple of hundred milliwatts. Yeah, and of course this is for the liquid-filled hollow core. And if you're working with vesicles or with cells, one would need to worry a little bit about the powers. You want to keep them fairly low, probably. But I think you can get significant trapping and propulsion even for fairly reasonably modest powers. But that's a question that the biologists don't seem to know the answer to. What sort of power can a cell support without being damaged? It's a bit like sunburn. I burn very easily, so I understand that.
Yes.
Maybe I missed the point. You mentioned that it would be possible to observe much kind of interaction at high velocity.
Yeah. Yeah. Oh, yeah.
More about that.
Yeah, I wish I could say more about that. So the idea is if this is vacuum and the particle's sitting in here, you could potentially accelerate with higher powers and maybe longer lengths or whatever. You could accelerate up to velocities that become quite close to the speed of light. And of course relativistic effects come in at that point. But there are people that have studied the interaction of electrons traveling very fast along a surface and coupling to the electronic states in the material alongside it. So there's people doing electron diffraction of surfaces and studying in that field. It's not a field I'm so familiar with myself, but John Pendry told me about this. He used to work on this. So if you have an electron going really fast along here at kind of subluminal or sort of close to the speed of light, then you can get very strong interactions with a kind of van der Waals interaction. It's not exactly van der Waals, that actually create drag forces on the electron. So it's not completely free just to accelerate as fast as it likes because of the presence of the solid material. And this would equally well be true of a lump of dielectric because it contains electrons and are traveling very fast. So at very high speeds, apparently you can get a kind of exchange interaction or interactions between the very rapidly moving particle and the walls of the waveguide. So it's a kind of fundamental experiment. I believe that we have a chance in this experiment of maybe observing these forces, because what would happen is that as we turn up the power and the particle goes faster and faster, we would find that there'd be an anomalous slowing down, that the particle would not just keep accelerating, it would slow down more than you would expect from relativity. It would actually, there'd be an additional drag force. So we could perhaps measure things that had never been measured before.
I was wondering, for this kind of experiment, instead of using a very long fiber, could you produce some sort of a ring?
Sure. Yeah. Yes. I mean, you can certainly coil the fiber in a circle. You need to be a little bit careful because as it goes faster and faster, the trapping force might not be sufficient to prevent it crashing into the wall. So there will be some kind of mechanical or dynamical condition on stability of the particle trapping. And actually the dynamics of the particle in the transverse plane are fascinating here because the force field that the light produces on the particle is not inverse square. It's not an inverse square force field, so you can't get nice planetary motion. You probably get chaotic motion in the transverse plane, or even more complicated things. I don't know yet, we haven't done the experiment. And working out the actual forces on the particle is quite challenging. Even to do that. And once you have the forces, of course, we could then work out the the dynamics. And it's more than that, of course. The particle can also be driven to spin by the light under certain conditions. You can actually get a net torque, a net moment, driving the particle to spin. So the particle may actually spin as well, in which case the dynamics becomes even more interesting. You get spinning tops being driven around, gyrotropic effects and so on.
Are there more questions? Yes?
How small can the particle guided fiber?
How small can it be? Well, there's nothing to stop it being very small. I mean, the smaller it is, the weaker the forces driving it, of course, will be. But that said, if you're operating close to a resonance, then the forces become quite big. So, for example, you could guide atoms and molecules in this way. You could get a certain amount of force and trap them in the light. You will have to be sure that KT, that the amount of thermal energy is not so high that the trapping force is not strong enough to trap, so you might have to work at cold temperature. So potentially you can trap atoms, so very, very small things. But for an experiment with dielectric particles, I mean, I think 100 nanometers is a reasonable sort of size. They could be a bit smaller. But the forces are reasonably large for 100 nanometers. But we've guided particles from, in these experiments, particle sizes were 1 micron to 3 microns or so in these particular experiments. And the core diameter itself, what was it? I can't remember. I think it's about 17 microns across the core. So the 5 micron particle sitting in that is quite a large fraction of the area.
Is it possible to use this method to build up some three-dimensional metal materials?
I don't think so. No. I mean, I think what we are thinking of doing is not so much metamaterials. Don't really work in that field. But something you could imagine doing, what's the best picture to use, is forget about the acceleration, but it's possible to. In fact, we've observed this already. We haven't reported it yet, but it's possible to trap a whole row of particles, have a periodic sequence of particles trapped. Because what happens? The light comes in, it gets scattered by this, and it actually focuses down to a spot on this side, and then you can get another particle trapped here, and another particle, another. So a whole kind of row of particles trapped and held together by the light. So if they try to move, they actually pull each other, a little bit like this. So it's a little bit like a monatomic lattice coupled together by the light. So you're using the light to provide the coupling force. So the dynamics you can imagine of a system like that, where the attractive and repulsive forces between the particles is produced by the light, is quite interesting. Which is kind of moving in the direction more towards optical lattices and Bose-Einstein rather than metamaterials. Maybe you can make a one-dimensional material that had some interesting properties here.
Small question. You mentioned about chemistry. Have you tried photochemistry in this?
Yes, we are. We're doing photochemistry actually.
So like putting CO2 and H2O and producing methane.
We haven't thought of doing that, but what we are doing is it's a bad picture to use, but the liquid. Let me go back to a picture with some liquid. So there's liquid in the hollow core. We've been doing experiments. Forget about particles, but just with photochemicals in here that where we launch laser light in order to photolytically initiate a chemical reaction, and then at the same time monitoring what happens, the rate of the reaction. We can measure things like the quantum yield of a chemical reaction, for example, very accurately. We're actually working with a team of chemists at the University of Warwick in England on this, and also in Edinburgh. So they seem quite interested.
20 years ago it was a big field.
Yeah.
It never started out.
All right. Well, maybe. Yeah.
I want to know the birefringence of the birefringence.
The fiber. What's the birefringence?
Yeah.
The value of the birefringence. It's you can get birefringence values of 0.1. 0.01, so it's about 10 times larger than you can get in a conventional fiber. So it's a lot more birefringent. The beat length is much shorter. Yeah. Okay.
Are there more questions? If not, let us thank our speaker for the wonderful. So now it's time for the lunch break, and we will meet here again at 1:30.